Okay, so this is a video, and I'm going to show some examples using the multiplication rule. And you'll see here, so again, the multiplication rule is when I'm selecting more than one. So you're going to see here maybe also examples regarding the multiplication rule and the addition rule, maybe an intersection of the two also. So let's see what happens. So let's say that I am, real quick, again, I'm using a deck of cards. So I'm doing a deck of cards because everybody freaks out with it. And it's not as bad as you think. You just have to be very consistent with how you approach it. Let's start with selecting two cards. And let's determine the probability that I select two, let's say the two cards are both kings. Let's do aces. I like aces better. Whatever. I mean, you have to automatically think, if I'm selecting the two cards, am I selecting one at a time? And if I am I putting the first one back and then selecting the second? Are they independent or dependent events? So I'm going to select them. Let's do it with replacement first. So I'm selecting the first ace, and then I'm putting it back, and then I'm selecting the second ace. That's called with replacement, which means that these events are independent events. So two cards, I'm going to multiply two probabilities, and the first parenthesis is going to represent the first event, which is selecting an ace. And selecting an ace, that probability is 4 out of 52. But I selected that ace and put it back, so I still have the same number of aces in the deck, and I also have the same number of cards in the deck. So when I select the second ace, I still have 4 of them, and I still have 52 total cards. So with independent events, it's easy to simplify this. I can also say 452 or 4 over 52 to the second power. So when I enter that into my calculator, parentheses, 4 divided by 52, close parentheses, and then raise it to the second power, and then I'll convert that into a fraction if I need to simplify it. 1 out of 169 simplified, so in exact fraction form, 1 out of 169, or approximately 0.006 or 0.6%. Now that's very, very low. I would say that that's small enough to say that that might not be likely. That's not an unlikely event. It's less than 5%. Does it make sense that I'm only going to select two cards and that it would be unlikely for them both to be aces? Well, think about that. Does that probability make sense for my situation? Which it does, right? Most likely we don't select two aces when we go and select two cards. Well, let's select 3 cards. And let's do the probability that they're all aces. Let's just do it again. But what I'm changing here is now it's without replacement. So now when I select the first one, I'm not replacing it and selecting the second one. I'm going to keep it out, then select the second one, and then keep that one out, and then select the third one. So what that's doing is changing the number of aces with each selection, and it's also changing the number of total cards with each selection. And that means that I have dependent events because the probability will change. Now I'm selecting 3, so therefore I'm going to have 3 parentheses. And my first parenthesis is the first event. So what is the probability of selecting an ace at first? 4 out of 52. Now I'm keeping that ace out. So now there's only 3 aces in this deck. And now there are only 51 total cards. So now the probability that I select another ace is going to be 3 out of 51. There's only 3 aces left because I kept this one out. There's only 51 cards left in the deck because I took one out. I took 2 out for the first 2 events. So now there's only 2 aces left out of 50 cards. So, be careful when you have dependent events. I can't simplify it the way that I did up here because each, parenthesis represents a different probability, different numbers. So when you do that, you're going to have 4 out of 52, close parentheses, times, parentheses, 3 out of 51, close parentheses, times 2 out of 50. And let's see what that is. And then if I use that, you're going to see a lot of, as we use the multiplication rule, a lot of these fractions will have large numbers because we're multiplying. So most of the stuff that you do will be represented in decimal form. But anyway, if you need the exact fraction, 1 out of 55/25, or approximately. So I want you guys to realize that this is 1.80. This is not my probability. E-4 represents scientific notation. This means 1.809954 times 10 to the negative 4. That means I moved this decimal 4 places to the left. That's the actual number that this calculator is showing. 0.0001, I'll just do 8. This is a very small probability. If I put that in percentage form, that's 0.018%. That is extremely low. I would say that that is very unlikely to occur. Well, does that make sense? If I have a deck of cards and there are 52 cards and only 4 of them are aces, does it make sense that if I pick 3 out and I keep them out each time, that I would get all aces? That probability is very low. That makes sense that that probability would be very low. So be careful. Let me go back real quick. Let's say that I select, do my last one. This is really, let's say that I select 3 cards, and I want the probability that all 3 cards are either let's just do an ace or a king. So this is a very interesting problem. I'm selecting 3 cards, so that means I have the multiplication rule. But over here, I have the OR case, and that means I have the addition rule. So this is the combination of the 2 rules. So I want you to first think about selecting 1 card and how to determine that. If I select 1 card, what's the probability it's an ace or a king? Well, let's do that. Are these 2 events, right, the OR case is addition, are they mutually exclusive? Yes, I don't have an ace and a king at the same time, so I do not have to subtract any intersection. There are 4 aces and 4 kings out of 52. So I have 8 out of 52 is the probability of getting an ace or a king if I'm only selecting 1 card. But now I want to select it 3 times. And let's do, for the heck of it, let's do it with replacement first, and then we'll do it without replacement. So here's with and without, just to show you the difference. So here we go again. I'm selecting 3 cards. What's the probability that all 3 cards are either ace or king with replacement, independent events? Well, the probability that each one of these cards is an ace or a king is 8 out of 52. I did that first. So 8 out of 52 is the probability that the first card is either an ace or a king. But I'm replacing it. So what's the probability that the second one is also an ace or king? It's the same. Independent events, the probability doesn't change. I'm selecting 3 cards, so that's to the 3rd power. Now, I'm going to go and put that in decimal form first. 8 over 52 to the 3rd power. Okay, I'm going to put that in decimal form. So approximately 0.004 or 0.4%. Very, very low. Very, very small. Which makes sense. Is it, likely that I would have an ace or a king with 3 cards? I mean, we like that. Depending on the game that you're playing, that would be an ideal situation. You get one of those high cards. Well, if ace is considered high, you get one of those cards each time. What if it's without replacement? Now I'm selecting 3 cards, and the probability that each selection is an ace or a king is going to be different because these are dependent events. Well, the probability that the first card is an ace or a king is 8 out of 52. But now I'm keeping that out. So now there's only 7 cards left that are ace or 52 out of 51. I took a card out, so there's only 51 cards. Now I took 2 of these out, so there's only 6 left that are either ace or king. And then now there's only 50 cards left in the deck. So let's see what that is. 8 out of 52. So that's 8 divided by 52 times 7 divided by 51 times 6 divided by 50. And I'm going to keep that in decimal form. So 0.003. So approximately 0.003 or 0.3%. I want you to notice that without replacement, the probability decreased. Well, that would make sense because I'm taking the card out and leaving it out each time. Be careful with this. So, it's a combination of the addition rule and the multiplication rule. But if you're selecting more than one, focus on one, deal with that, and then go and deal with more than one. Okay? I want to do one more just because let's say that I'm selecting 4. cards. And I want the probability that I select them in this order. I get a king, then an ace, then a jack, and then another king. Without replacement, I'm expecting this to be really small, but let's see. That would be ideal also depending on the event or the type of game that I'm playing. But selecting 4 cards without replacement, so at their dependent events, the probability of each case might change, will change. But let's start with the first event, and that's selecting a king. So while selecting a king, there's 4 kings out of 52 cards. I keep the king out. So now I only have 51 cards. But I kept the king out. I still have 4 aces. Taking a king out does not affect the number of aces that I have in the deck. So be careful with that. This time it didn't decrease because I'm selecting a different card the second time. For the third time, I still have 4 jacks. That's still not changing, but I only have 50 cards left in the deck because I took the king and the ace out. Now I took a king, an ace, and a jack out, so I only have 49 cards. But I only have 3 kings left because one of them were over here or was over here. So just be careful when you do those calculations. Be careful. And order matters. Order matters. Let's do 4 out of 52. Order matters with the multiplication rule times. What was it? 4 out of 51. And then it was a jack, so 4 out of 50. And then another king, so 3 out of 49. Yeah, I expected that to be small. So, move that decimal 5 places to the left. So this is approximately 0.12345. In percentage form, move this 2 places to the right. And now I have 2 zeros, so 12296%. Extremely unlikely for me to have the situation where I'm randomly selecting 4 cards. And I'm not replacing each card. And I get this particular order, king and then an ace and then a jack and then a king. I mean, it makes sense that that would be extremely low.